All right, so apparently I am recording now. Let's get the cursor out of there. Okay, I have an announcement and a request to make that when students meet, like on Saturdays or whatever is your time that you get together, invite everybody. We have DBMD students that are a little shy, so I would like them to be involved. I would like them to be in the group. So reach out, use Canvas, communicate, email, I don't care how you do it. See if you can organize it. All right. Now, do we have any questions specifically? You mentioned you might have something.
So I read your response from on Canvas, and I think I have the right idea, but I'm not entirely sure.
Sorry, I don't know where else to put that one.
I'm not entirely sure if
Okay.
the picture I have is correct. I think it was that one, the bottom one. That is the right
Okay,
track.
so let's see. Actually, why don't I put it on the board and then it will be on the video and all
Yeah, I
that
was
stuff.
gonna say.
So
I
what's
was
the
actually just
problem?
gonna say
One?
that. That was the one. It was like provide an example of a counterexample that if the production set is non-convex.
If V of y is a convex set for every y, it says. He doesn't say for every y, but he implies for every y. Then the associated production set y, big Y, must be convex.
Yeah.
All right? So he has the simplest possible counterexample. Basically, I like this because it relates also to quasi-concavity, which is very important in the consumer theory, right? Now, quasi-concavity does not imply concavity. Concavity implies quasi-concavity. All right? Now, what's the concavity I'm talking about here? Doesn't it say convex?
Right.
Well, I haven't lost my mind quite yet. A production function, if you only have one output, right? If it's corresponding to a convex Y production set, it is pretty much by definition a concave function. Let me illustrate that. Who remembers one of the definition of a concave function that I gave you that refers to the subgraph? Yes? Anybody? Bueller? Some people have seen the movie, okay. All right. A function is concave if and only if its subgraph is a convex set. As simple as that, right? Okay. Now, a production function, if we have, input over here and output over there. Now, if we write a production set like this is the uppercase Y, right? Then observe, I've included the fact that you might be destroying things by accident, right? That's the ultimate free disposal assumption. Mathematically, it doesn't really make much of a difference. You would never operate down here. It makes no sense, right? So all the action would be here. But we might define our Y set to say, well, any arbitrarily large in absolute value negative numbers can be obtained. If we do that, and even if we don't, suppose we do it as he does in the book, where he stops it here, right? Right?
Mm-hmm.
Then, if this is a convex set, right? Then extending it down, I needed to extend down because I want to talk about the subgraph, right? And the subgraph is the graph of the function and all the points down. So the subgraph is this. So this would be the graph of the function f, the production function, remembering that we're measuring the input negatively, right? And this is the subgraph of f, right? All of this going all the way down. Now, as you can see here, if I already know that the part above the axis is a convex set, then I tag to it this orthon down here. It's still a convex set, right? That's actually fairly simple to prove. But I'm not even interested in that. It should be pretty obvious. It's a convex set. So decreasing returns to scale convexity of the production set comes with concavity of the production function automatically. All right? So, okay, a concave function, what sort of upper contour sets does it have? Because V of y is an upper contour set. Right? By definition. It tells you you need to produce at least as much as y. Now find all the input combinations that will allow you to do that. So it's the isoquant and everything above. Right? Okay. Now, if we only have one input, the isoquant becomes kind of a very trivial thing. It's a one-point set. Right? So for example, suppose I tell you, produce me this. So you give a particular number, y2 hat for the output. What is the isoquant? Well, you will go over here, right? And say, okay, project it down to the space of the inputs. The isoquant is this point. All right? What is, yes, makes sense? It's the most efficient way of producing that requested amount. If you use any less input, then you won't be able to produce it. But you don't want to use more input because then you're wasting money, essentially. Okay? Now, so the isoquant is this point. What is the upper contour set? Well, it's the isoquant and all points in the input space that are larger. Here, larger means go negative, okay? We're over that, right? We were not confused. So the upper contour set is this half line, starting and including this. Okay?
In the case of not making that restriction at y2 hat, though, it just becomes the entire line, right?
Define it.
So without, if we didn't say, okay, if we were just looking for the general upper contour set of this production function.
Any upper contour set has to be defined at the level of the function. This is what it means. It's the points in the domain of the function that achieve at least that much level when you plug them into the function.
Okay.
Right? So you have to give me an output amount. Otherwise, this thing is meaningless.
Fair.
Okay? Got it?
Yeah.
Okay, good. So, observe this set. It's a half line. Does it matter if I chose y2 here or a little higher or a little lower? It's going to look exactly the same, right? Do I agree? Okay. So, is this red half line, is it a convex set? I don't.
I'm looking for a magic marker, but I won't steal yours.
Good.
I'll steal them from someone else.
Good job. It's a convex set. Do we agree? If you take any 2 points in it and you put a linear segment that connects them, it falls on top of the set, so it's in the set. Right? Okay. Yeah. So this essentially illustrates, doesn't prove, but illustrates that if a function is a concave function, its upper contour sets are convex sets. If I will attempt to connect this now to the utility story, right? Now suppose, how would that look? And this is where I go into really dangerous territory, attempting to draw in 3 dimensions. But I will try. We're not going to need this axis very much, so let me truncate it a little bit, so I'll have more room over here. Now for our consumer, right? Let's see. Let's not do it that way. It's my attempt to do perspective that is tricky. So suppose you have two goods you're consuming. So you have X1 and X2. And up here, I'm going to put the level of the utility you achieve. And let me attempt to draw the graph of a concave utility function, which would be kind of a hill going like that, right? So let's see if the green works. It's going to look something like this. And to try to let you see the three-dimensionality of it, I will also select a level of utility and show you how you find the indifference curve, and therefore the upper contour set. What you do is, of course, you go here, and now you go here with a plane parallel to the domain, the x1, x2 plane, right? So if you take a plane, which, oh gosh, is something like that, if you can imagine it horizontal, okay? It's going to cut the graph, and it's going to cut it in a way that kind of looks maybe like this. Now, what you do here is you take the projection of this down into the x1, x2 space, and now you have an indifference curve. Okay? Take some time to absorb it. Let me know if it's not clear. Questions? Okay. What is the upper contour set? Well, if I tried to choose any utility level higher than the U bar, I would be hitting this somewhere on this side. So it would fill out, the projection of it will be here. So this is the upper contour set. Okay? Now, incidentally, if you want to think of this as a production function, x1 and x2 are the inputs. U is what you write for the output. And you measure the inputs positively rather than negatively. This is like a two-input case illustrating that, right?
Yeah.
So, in this case, if the function is concave, as I have done, the upper contour set for any level is going to be a convex set as well. So it's a fundamental theorem. A concave function, all its upper contour sets must be convex sets, but it doesn't go the other way.
Right.
Right? I haven't illustrated that it doesn't go the other way yet. Okay? So are we okay so far? Okay. Now, let me now draw here another production set, right? And this other production set I will draw in blue. And I will make it not be a convex production set, right? But I will show you that its upper contour sets, the input requirement sets, are all of them convex sets. So, here it is. All right? All right. You see, this blue production set is not convex, right? You can take a point here, you can take a point there, you connect them, you're outside the set. Okay? We're all okay? Okay, good. So, let's find an input requirement set, kind of generic one. In fact, since I've had here the y2 hat, why not do it? Go here, come down here. It's a half line again. Oh, interesting. input requirement sets of the blue production set, and therefore the blue production function, which is not a concave function because its subgraph is not a convex set. Nevertheless, all the upper contour sets, which are all the input requirement sets, are convex sets. So, we call this a function whose upper contour sets are all convex sets is called a quasi-concave function. So this is a quasi-concave function just as much as that one was. But the blue one, as a production function, is not a concave function. Okay? This can also be demonstrated here. And the way he does it, he gives you an explicit in the answer key.
Yeah.
An explicit example. Well, this is the x square function,
Right.
right? But this is the kind of picture you want to have.
Okay.
You have a solid idea of what is the input requirement set.
Okay.
Okay? Let's do it here. What shall I do here to illustrate a quasi-concave but not concave and difference utility function, right? I need to bend that way, right? Rather than this way. So, the way I can make you perhaps see the best, and this is really tricky, so bear with me, is to imagine I wrote this as an attempt to indicate where the graph is. And then I drew this to indicate that it really is a hill, right? Okay, so this line would be like taking a line in the space of inputs, taking a plane that is defined by the vertical axis in this line and cutting across the graph. So it's a vertical slice. And the indifference curve comes from a horizontal slice projected down to the domain. The vertical slice is just a slice of the graph. And from that you can see that we have a concave function. If you reduce it to just this little domain. In fact, that's another property of concave functions. If you have a concave function of more than one arguments, every vertical slice produces a concave function. Okay? So now that gives me the hint how to get from the, to do the same thing I did here, to give you one that is quasi-concave but not concave. So I shall still imagine how the slice will look, the vertical slice, over a line like that. And suppose it looks like that. But I want to illustrate how its indifference curves will look. So if I take this plane, this very same plane, right, it would hit it somewhere here, but still in this fashion, right?
Yeah.
So the projection will give me an upper contour set that is still a convex set. Basically for the same reason it happened here. This is too constricted because you only have one dimension in the domain, but the principle is the same. Okay? So you can have, even with multiple arguments, a quasi-concave function that is not concave.
Right.
Okay.
Okay.
In fact, if you have a function of only one argument, if it's strictly monotonic, either increasing or decreasing, it's automatically quasi-concave. Because its upper contour sets are going to be half lines. Think about it. And so immediately it tells you, oh, it really is very weakly connected to concavity. Concavity implies quasi-concavity, but quasi-concavity is quite a bit less demanding requirement. And the whole point of that exercise was to get your hands dirty in getting really how it looks. Questions? Any questions? Okay. So, right. I have posted on Canvas practice problems for the next midterm. They basically require you to have require us to have covered cost minimization. But I think I can talk about them already because we covered cost minimization in a sense. How did we do that? We did expenditure functions for the consumer, which mathematically is the identical problem with not a whit of a difference. It's exactly the same mathematical problem. You have an upper contour set, you're minimizing a linear function over it. Okay, so still recording. So paranoid after that time. All right. So, has everybody seen the practice problems?
I
Okay.
saw that they were posted.
Okay. Download them and start looking at them. They're not that hard. They're not that hard. The first one is a sort of Slutsky equation for the production function. Sort of. All right? So I'll give you an intuition or a story, and I will let you figure it out as I give actually fairly detailed directions on how to do it. And here is the intuition. Suppose you have here your inputs, and I can only do it, of course, for 2 inputs. The general argument works just fine for however many, but I couldn't make a picture. And so I choose some level of output. Okay. And I choose a price ratio for the inputs, which is given to me, right? And I ask myself, okay, how do I find the cost minimizing combination of inputs if I am required to produce this level of output? So the picture here is, of course, not a surprise. You're going to take lines, isocosts, parallel to each other because they all correspond to the same price ratio for the inputs, and you're going to push them as far down as possible until you cannot go any further, and you find the optimal cost minimizing x1 and x2 star, which depend on W, the vector of prices of the inputs, and they depend on y, right? Because the whole problem is set up as follows. You have a y you have to target, and then given that, how can you produce it most efficiently? That's not the same as profit maximization, but it is quite connected to it. For one thing, if you want to profit maximize and you're a price taker in all markets, including output, then profit maximization implies cost minimization, right? Because if you're wasteful in how you produce, you can't possibly be maximizing profits, right? But they're not the same thing because in profit, the profit function, if you recall, depends on the price. Let's say we have output and inputs, so we have the same notation, but it only depends on the prices. It does not depend on an amount of output because you decide how much to produce when you're maximizing profit. It's not a constraint. Okay, so we now ask the following question. Imagine, let's say for x1, imagine a small change in W1. Let's say, for example, W1 is reduced a little bit, so it becomes a little cheaper to produce, to use x1. Okay? So the isocost is going to tilt a little bit, get flatter. Now, what will happen here is if you're looking just at the effect on the constraint problem, that is the cost minimization problem, right? So we had here a decrease in W1 is what I'm illustrating. Then it's clear what to do, just like with the Hickson demand. You're going to use more X1 and less X2, right? The less X2 doesn't necessarily extend if you had more inputs, but definitely you were going to use more of the good whose price went down. Yes.
Is that under the assumption that the two resources are easily, you can substitute either one for the
As you can
production
see,
of that?
yes.
Okay,
For example, if I had Leontiev,
right. That would be
you
different.
would
That'd be
keep
another-
using the same amount,
Yeah,
right?
okay.
So yes, as long as there is some substitutability, and there is the way I do it.
In this case, yeah.
Right?
Okay.
Okay, so then if we ask the same question of the unconstrained problem of profit maximization, we realize that something else might be in play. So let's think. For the Slutsky equation, a price change, let's say that one good got cheaper, to mimic this example, did two things to you. It made it relatively cheaper to use that good, to buy that good, in this case to use that input. So that's captured in the cost minimization story or the expenditure minimization story with the consumer. But in the consumer, it also made it more, it gave you essentially more purchasing power. And so we had the income effect, right? Here we have no income, but there is a constraint here. We have an amount of output that we are constrained to use if we're studying the cost minimization problem, right? Because the problem starts by saying, here's an amount of output. How can you select your inputs to produce it most efficiently without waste of money? All right? So we're not going to have an income effect because there's no income, but we might have an output effect. So in particular, let's follow the following intuition. And I'm not going to draw anything more because I'd like you to draw it and figure out the math expression of that, which is actually easier than you think. Don't overthink it. But the story is it possible that the drop in the price of input 1 might motivate you to sell more, to produce more Y, or less? It might, if it makes it cheaper, your cost goes down, right? For any particular Y, because it's cheaper to use one input. So you might want, when you re-maximize your profit, right, you might want to sell more. Aha. So then we'd be looking at not only sliding down a given isoquant, but also moving the isoquant. Okay? So now you see the connection here, logically at least, between the cost minimization and the profit maximization. And you see why the problem mentions something called the output effect. Okay? I will leave it at that. I will also drop the following heavy hint. There are a number of textbooks, but not Varian, that have it. It is not a crime to go find it and figure it out if you can't do it yourselves. Okay? But I hope that what I gave you actually is enough of a conceptual framework that it wouldn't be too hard to understand why this is an identity. And once you understand the identity, what the heck, take derivatives on both sides. We've done that, and if I'm asking you explicitly to do a Slutsky-like thing, then if you look at the Slutsky derivation, it was starting with an identity and taking a derivative. So what I'd like you to do is to do that and then interpret every term appropriately. Where is the substitution effect? Where is the output effect? Okay? Now, the reason I wanted to tell you about this is that problem 2 requires it. It requires that identity. And if you use this identity, problem 2 is extremely easy. If you don't know this identity and it's not in this book, then problem 2 might be hard. You would have to reinvent problem 1 on your own. But so I thought, well, I'll give it to them. So I did. So problem 2, I gave you a hint. Use Hotelling's lemma, and then see how you can use this identity. All right? So I won't say too much more about that, because I think given that, chances are you'll figure it out now in just, 10 minutes. So, well, possibly 15, but not much more, seriously.
Why doesn't Varian cover that?
That was a bit of a surprise. I think you always have to cut something.
I guess, and I feel like that.
I
feel like that's an important concept. I mean, it sounds important enough.
Yeah, you have to
Such
cut
as-
something. There's
right.
just no way to put everything in.
Right.
Maybe he planned to give it as an exercise to his students, and always has done that. Who knows?
Yeah.
But I don't know him.
Yeah.
And I haven't gone up to him. I mean, I met him once when I was a grad student, and I was presenting at a conference in Michigan where he was a professor at the university. And my advisor introduced me to him. Would be a good person to know for me going to the job market in a few months. And so I had a nice, pleasant conversation. I was completely overawed by him. I didn't quite know what to say. And that's my entire interaction with Hal Varian is this. So I don't know why you didn't put it there. I had, like pretty much everybody else, has studied this book and his undergraduate book. So it was like being introduced to this super duper guy, and I was like, I was not going to ask him, why did you not pick that?
Yeah, I suppose that.
How dare you not put that in your book? Okay. So I think 1 and 2 are fine. Be careful when you use Hotelling's lemma. Because here, well, be careful how it is applied for inputs and for outputs. Remember that it is the way it's given in the book, inputs are negative. So Hotelling's lemma for an input will be the partial derivative of the profit function with respect to that input's price, but with a negative in front. Right? So given that, you should have really, really very few problems combining the identity of problem 1 and what I give you in problem 2 to solve problem 2. Problem 3 is math. Do the minimization problem. Use Contacker as needed. That's all. Problem 4, similar. That is actually more of an economic problem, because you're going to have to always be asking, the firm has multiple plants, and you are given a very simple form for average cost, a linear affine average cost for the various plants. And you want to think as an economist here, more than mathematics. Yes, you can do the whole thing mathematically, but you want to argue, make some pictures. You want to use the plant that, given the configuration in particular sub-question, will give you the smallest cost. So write the total profit, see how it relates to those average costs, and make the story from, okay, you want to use the cheapest plant that you have. And that story gets you pretty much to the entire answer of this. Okay? Problem 5. Problem 5 is actually kind of similar combination of these things. You have 2 technologies. One is Leontief, the other is linear. And it requires you to find, it asks you if they have constant returns to scale. Very easy, I'm not going to tell you anything about that, just do it. Find the cost function, do the minimization. Again, right? Be very, very, very careful. The Leontief, the first one, doesn't have derivatives at the kinks. So don't attempt to take derivatives. That's like a mistake I really don't want any of my students ever making. If it's Leontief, it's not differentiable, don't you dare take derivatives. and then try to argue. I've seen it in prelims. And it makes me really depressed when I see that. Don't do that on your prelims. Or ever. So what do? Make a picture. Right? You know Leontief will force x1 and x2 to be the same. Use that. Right? Okay, so we have that. The other one is differentiable, it's linear, but you know it's going to involve a lot of corner solutions. It's a perfect substitutes case. So use for Kuhn-Tucker for that one. It gives me all the right conditions about when is it going to be that this good is 0, or this input is 0, that input is 0. There's only 2 inputs, it's not that horrible. Okay? And once you have figured out the cost functions, right, then the last part of the problem says you have an order to produce a particular given amount Q bar. How should you allocate it between your two plants? Give it to the cheapest one, right? But you need to have the expression for your cost function before you can do anything. Which is why the first and the second part of the question has you calculate that. Now there are numbers involved here, so you'll actually be able to compare the cost of producing Q bar with this technology, that technology, and see, do you want to give to both plants some part of it? Do you want to specialize and send it to one plant or the other? And what wages, W1 and W2? There will be some inequalities that if one inequality holds, it tells you this plant is cheaper. And if the opposite inequality holds, that plant is cheaper. That's the kind of thing you do here. So it really, really, really is not rocket science as long as you can do minimization and figure out the cost function. Okay? Any questions? All right. So that pretty much covers it because I said I gave you big hints on everything for the practice problems. Now I want to give you small hints for everything in chapter 3 that you have homework for next time. Right? That's our next homework. I think 3.1 through 3.2, 3.3, 3.4 is for the MA students, and then you get to do 3.5.
Yeah.
Okay. So let's look. 3.1. Oops, too far. You have a competitive profit maximizing firm with a profit function that is separable. It's one function of one wage, one price of input, plus a function of the other one. All right? So, two questions. What can we immediately know about the first and second derivatives of each one of those phi subfunctions? What do we know about the properties of a profit function? We did it Tuesday. Is it increasing, decreasing in W1 and W2?
Is that a hypothetical or do you want an actual?
Oh, I want the question, an answer.
Oh, okay.
What do we know? Do you remember? Yes.
It's increasing.
Increasing in prices of inputs. Careful.
No, I'm sorry. It's
The negative comes
yeah.
in. It's not increasing
Yeah,
in input prices and not decreasing in output prices. Right? That was property 1,
Yeah.
Tuesday night. What else do we know about it? Is it convex? Is it concave?
Concave.
No, convex.
Yeah.
Convex, which is
I'll get there.
that strange example that he has with it seems counterintuitive at first, but then as you think about it, I hope it works.
Mm-hmm.
In other words, the farmer, would they want to have some sort of insurance about the prices or just adjust every time? So that should tell you, if it's convex, that should tell you something about the second derivatives of every one of those phi functions. So that's easy enough, I think. B, how about the cross derivative of the demand of one factor when the price of the other one changes? Now that ought to be an extremely obvious answer. Anybody want to venture an answer? Yes.
I don't know. I'm 0 for 2 right now. I'm 0 for 2 right now, but I'm
Okay. What do we know about Hotelling's lemma? How do you find the demand for, say, input 1 from the profit function? You have the profit function. You take a derivative with respect, say, for x1, you will take the derivative with respect to w1. Given the form of this profit function, in the result, will there be a w2? Will there? Look at it.
Oh.
No.
No.
So the cross partial derivative of the profit function with respect to first w1 and then w2 will be 0.
Right.
Okay. Okay, 3.1c. Argue as follows. Can the marginal product of a factor of production depend on anything but the amount of that factor used? Take your answer from there. I'm not saying more. 3.2, it says, consider the technology described by y equals 0 for x less than 1 equal to 1, and then log x, and then calculate the profit function for this technology. I'm going to make you a little picture first. Oh man, these are not the best markers. Go back to my trusty brown one here. Oh, the green one is the same kind. So, basically, you should always receive great delight when the formula you are given makes it possible to make a picture. Right? And here we have one input and one output. So it's definitely easy to graph the production set and see what on earth you have. Right? So he says, y is 0 for x is less than or equal to 1, and then y equals the natural logarithm of x for x bigger than 1. Calculate the profit function. Okay. So, I will write x as negative minus y1 again, because I would like you to get used to the idea of the production set being here. So x equals 1 corresponds to y1 equals to minus 1, right? And now he says, for x less than or equal to 1, that is y1 greater than or equal to minus 1, so anywhere here, we are at 0. Right? Beyond that, the natural logarithm of x. Natural logarithm of minus y1. Minus y1 is negative, so now what do we know about the logarithm? It is in fact attaining the value 0 when the argument is 1. Below that is negative. So they've taken the logarithmic function and chopped it off at 0. Because, of course, negative outputs would be kind of hard to interpret meaningfully. Okay? So here's your production set. All right? So, I didn't shade it because it's not shadeable, but this is included. All the way to here. Remember one of the properties of the production set, possibility of inaction? Can always shut down. So suppose, now what I'm going to do is I'm going to imagine different price ratios, price of input and output, and kind of show you where the profit maximization will occur. So if my price is like so, a slope like that, and my maximum occurs here, right? And you can always look at the intercept on the vertical axis to get a visual on how big the profit is. Well, this profit is negative. But that's not the problem. Is that really the maximum profit? No, the maximum profit is 0 because you could decide to do nothing. So in other words, it's misleading to draw it like that because this first order condition is actually irrelevant for this problem because look at the maximum. It's here. It doesn't involve a tangency because of this bizarre way that the production set extends. By the way, is this a convex production set? Mm-mm. It is not, right? So you can write, a point like that and a point there, and they are not. The interval is not in the set. Do you have any? Do you think you have an expression you remember from principles that connects to this? You need to have at least one unit of input before you produce anything. Did you learn anything that kind of rings a bell? Fixed cost? See, you knew it. You need to have a certain amount before you can produce anything. All right? But it's not a sunk cost because you can decide not to produce anything, which allows you to have this whole segment. Okay? Okay, take it from there. I've given you plenty. Basically, if my brown line was very flat compared to the one I started with, oh, this thing now is going dead on me. My maximum will be somewhere there, and then it will be relevant. What is the tangents in here? And I'd work from that. Because then my profit here will be this. So figure out how to express all that, but they gave you basically 80% of the answer, if not 90. But I will be looking for your argument on how you explain it, okay? 3.3, totally and completely computational. You have a production function, find the profit maximizing demand and supply function. So find the profit function and use hotel lengths, yeah. For example. Or just do it directly from maximizing profit and do the first order conditions and so on. Check the second order conditions, by the way. Argue for all of maximizations and minimizations you have, why you think you actually found a maximum or a minimum, whatever you need. 3.4, Cobb-Douglas asks pretty much for the same kind of calculation. Do it. I don't think I need to give you. I don't think I ought to give you a hint. 3.5 is kind of a Leontief, but raised to a power. Think about it. Does it really change anything about the isoplans? It does not. Take it from there. All right, I am done with how much I was going to tell you. Now I would like to know if there's any other questions. All right.